Can you speak about?
I'm very happy to be here, and thank the organizers for the invitation. My congratulations and best wishes to Leonid Pastor. So the work that I will talk about today is on classification and symmetry properties of scaling dimensions at Anderson transitions. So it's work in collaboration in Ilya Grusbeck and Martin Zirnbauer. Both are here, and partly also with Andreas Ludwig. So there is the first part, which was published in PRL last year. The long paper, which contains much more and which will be the main subject of the talk, is almost finished. So we are just kind of polishing it, and I hope it will be available in the archive on the scale of days. Yeah, and I think it's so I've chosen this work to report here in particular, since I think it fits very nice in the subject of the conference, but also actually we started this. It was initiated in a certain sense by discussions 4 years ago here at the Newton Institute, and so now I think we want to report what happened in 4 years. Well, actually, discussions, but then they was kind of forgotten for a while, but then we revived. Okay, so yeah, and I want to mention another related activity. I will briefly sort of describe it during the talk with, so this is my joint work with Igor Burmistrov and Igor Gorny. So Igor Gorny is also here, and also with Schumann and Ferdinand Evers, which is also recently published. And also I will show some unpublished numerics by Ferdinand Evers and Schumacher that is related to the subject of the talk. Yeah, okay, so I will start with some introduction on Anderson localization and multifractality. Well, we all know that Anderson's works that strong disorder, sufficiently strong disorder, leads to localization of quantum particles. So what happens in the sort of weak disorder regime depends on dimensionality, and that was the subject of scaling sort of arguments in 70s, Saules and Wegner, and the famous paper by Gang of Four led to this picture, which shows the scaling functions, the beta function, logarithmic derivative of conductance over the system size as a function of the conductance, with the prediction that in 1 and 2 dimensions, so in 2 dimensions below, the flow, this derivative is negative. It means that the system, the conductance flows towards small values, so the system becomes an insulator in the thermodynamic limit, whereas above 2D, say in 3D, there is this critical fixed point, so that above this point we flow to the metal, to large conductance, and below we flow to the insulator, which means there is a metal insulator transition from delocalized to localized phase when we change disorder, and it goes through the critical point of the metal insulator transition, and this, what happens at this point, will be the subject of the talk. And like the previous speaker, I cannot resist the temptation to advertise my review on the subject with Ferdinand Evers several years ago. Yeah, so the field theoretical approach to the problem is based on the nonlinear sigma model that was in this context pioneered by Wegner. So the action of the sigma model is shown here. So the sigma model is a field theory. So and so the action is a sort of weight of on the statistical mechanics language, is sort of weight of different configurations of the field. So the it looks actually pretty innocent. It's quadratic in Q, so it would be, of course, then trivial. However, it's not, since there is a constraint on this Q, so Q belongs, so Q squared is equal to 1, which means that Q belongs to certain manifold, which is kind of sphere, but it's more complicated than just a sphere. It is a symmetric space. As an example, for the case of broken time reversal invariance, what we call unitary class, so that's a kind of technically simple situation. This manifold is so the symmetric space is the one shown here, and one needs to take a limit n to 0, which is a sort of replica trick in order to which should be done because we want to average our quenched disorder in this formalism. Yeah, there is an alternative formulation. Yeah, so that was sort of using so-called bosonic replicas. One can start with fermionic replicas, and that was done by Yefedov, Larkin, and our chairman. And then one gets a compact manifold. So for this symmetry class, it will be this one still with replica limit. One can combine two approaches, and this is a supersymmetry approach by Yefedov. And in this case, the manifold is a kind of product of these two, in addition dressed by anti-commuting variables, so product of compact and non-compact parts. However, there is no replica trick anymore, no replica limit anymore, and now then remains just integer for minimal models, just 1, or maybe also larger than 1. But so this is mathematically much sort of more solid than the replica approach, of course, although they are equivalent on some level of perturbation theory, but in general this one is, and it will be important for me. I will sort of use this supersymmetry, this mathematically more solid formalism in this talk. Yeah, and I also would like to mention that there is a generalization of this in the case of interacting problem, this which is due to Finkelstein, who is also here, and this will be used in talks by Igor Gorne and by Pasha Ostrovsky later in this conference. Yeah, this picture I think you have seen already before, maybe even twice. So what I want to emphasize here, this what I will say applies not only to metal insulator transition, but also to somewhat different version of localization transition, namely transition between different phases of a topological insulator. And the most famous example of such a transition is the one between plateaus of the quantum Hall effect, between quantum Hall plateaus. So there is this peak in the longitudinal resistance here, which corresponds to the fact that when you go from one plateau to another one, which are characterized by different number of H states, you go through the state which is sort of delocalized in the bulk, but it's not just delocalized, it's not simply delocalized, it's critical. It's also critical point, which has very similar properties to the metal insulator transition point. And sigma model, yeah, so there is a corresponding sort of flow diagram, which is now 2-parameter, and that was pioneered by our chairman again, and then the field theory was proposed by Pruskin, which is a sigma model now with additional topological term. So the sigma model approach also applies to this type of transitions. Okay, now what is multifractality? That will be sort of the key notion for my talk. So let me just briefly remind this. So let's take a wave function and raise it to certain power. So take it modulo squared and then raise it to certain power q. So q doesn't need, so it's a moment, but q doesn't need to be integer in general. It can be any fractional number, doesn't need to be positive, and in fact doesn't even need to be real, can be any complex number. Right? But here at the moment, so for this slide, let's assume it's real. Later it will be even any complex number. The corresponding, yeah, this called sort of inverse participation ratio. Yeah, we also integrate over the system size. It's not very important. Let's take the average of a disorder and see how this thing scales with change in the system size. Yeah. So there are two simple limits. So if you have an insulator localized states, yeah, then it doesn't scale at all, yeah. So wave function just sits somewhere, and so you get doesn't depend on the volume, yeah. For delocalized states, yeah, metal, it's a scaling very simple. It's just wave function is just more or less spread over the whole system, so it's a trivial scaling. But now at critical point, there is something intermediate. There is a power law scaling, but power law is non-trivial. It's neither this nor that. And these are sort of fractal exponents. And for each Q, we have a new exponent. And they are, in general, there is no simple relation between them. And this is why it's called multi-fractality. Yeah, so from discussions with mathematicians, I have an impression that this critical state sort of corresponds to this singular continuous spectrum that already was discussed here. Whether it's always correct statement or not, that I don't know, but at least there is apparently some connection. Yeah, yeah, so this, of course, corresponds to point spectrum, and this is to continuous spectrum. Now, it's convenient to split these dimensions in the normal part, like in metal, and the rest. So the rest, let's delta Q, and let's call them anomalous. They will appear later. One convenient way to represent the spectrum tau of Q is by its Legendre transform, which is called f of alpha. And the meaning of this f of alpha is essentially a distribution function of wave function amplitude on the logarithmic scale. So more a formula, L to the power f of alpha is measure of the number of points of the set of points where the wave function scales as L to the power minus alpha. So in a delocalized state, this function f of alpha is just a infinitely narrow needle. Yeah, it's just because the only alpha which is allowed is just d, because the wave function scales everywhere like one of the volume. So it will be just this needle. At a critical point, this thing broadens. Yeah. So some comments. So first, multifractality implies very broad distributions of observables characterizing wave functions. So as an example, parabolic f of alpha implies logarithmically normal distributions. They are very sort of broad distributions. On the field theory language, this delta Q are scaling dimensions of composite operators. This was again pioneered by Wegener, and this will be sort of one of key subjects of the talk. So we have, in fact, it's very non-trivial fixed point, this Anderson transition point, because we have infinitely many operators with negative scaling dimensions, which are relevant in the RG sense. So multifractality determines not only scaling of moments, but also scaling of correlation functions with distances between the points, like these 2-point correlation function can be multi-point. So all these complex scalings are characterized by these exponents. Yeah, one can also define multifractality as the boundary of a critical system, and this will be a different set of exponents, but I won't. Yeah, that's a joint work with also Ilya Gruzbek, who is here, and several other collaborators, but I will not discuss it. So this multifractality is a sort of fingerprint of given Anderson transition critical point. So for any other critical point, it will be sort of different spectrum. For example, if you consider Anderson transition in different dimensionality. So for each dimensionality, you will have some spectrum. Yeah, there is a sort of universality. So for given dimensionality and given symmetry class, there will be one spectrum. But if you change dimensionality, it will be another spectrum. So for quantum Hall, another transition will be another spectrum for and so forth. Yeah. So as an example of what is shown here, what happens with this multifractality spectrum when we change dimensionality for Anderson transition. So yeah, for example, if you look here, this is what is shown here is a function f of alpha. And you see there are several of them, and they correspond to dimensionality changing from 2 plus epsilon with epsilon equal to 0.01. And this is just calculated analytically up to 4. So this is 3, and this is 4. The broadest one is 4, and the 4 calculated already numerically. So you see this the spectrum f of alpha becomes broader and broader, which means that at critical points fluctuations, when you go up with dimensionality, fluctuations become stronger and stronger. Wave function becomes more and more fractal. So
what does it mean for the dimension to be 2 plus epsilon?
Yeah, well, So you can do two things here. So one, of course, this is of course an analytical calculation. So you can just formally do this renormalization group. It's usually epsilon expansion, and it's in this particular case there was a 2 plus epsilon expansion, so the dimensions are controllable near 2 dimensions. But in principle, you can also define as you just should take a fractal of the dimension 2 plus 2.01. You can take a fractal and consider localization problem on this fractal. And this has been even done. There have been numerics.
Then you have to define what does it mean, because there are fractals like trees, and there are fractals with loops, and they should behave differently.
Yeah. Okay. So let's put it this way. So what's shown here.
Let us proceed.
Yeah, let's proceed. So once again, what is shown here is analytical results of 2 plus epsilon expansion and 1 loop. And people looked at this at some fractals, let's put it this way, and that was consistent with this result. But that's a good question, that whether how sort of unique is this the definition of this fractal. Okay, good. So that's how sort of visualization of such a multifractal wave function as a quantum Hall transition point. So what is shown here is just one particular wave function, just chosen for certain realizational disorder. And so you see, so this means that, so this is just a space, 2-dimensional space, and this means that wave function here is large, and blue means that it's very small, and green is something intermediate. And so yeah, you can see this sort of multifractal structure that it's neither normal localized function, because you see the peaks on different sides of the sample. It's also not normal delocalized, because most of the space wave function is very small. That's it. Yeah, okay, good. So yeah, let me mention that experimentalists during recent years have some interest to this, and there have been several papers during the last couple of years where experimentalists tried experimentally measure, to see this. I think the success was sort of partial, I would say. They have seen qualitatively similar structures with strong flux, so looking similarly to what I showed before. However, they also tried to sort of extract this f of alpha there, and this f of alpha was quantitatively sort of way off what we would expect for the corresponding transitions, probably because it's in fact very difficult to be in sort of at the transition. I think that's probably we're not. I mean, there's apparently some experimental problems, but I think it's just to emphasize that there is an activity in this direction, and just show you some nice pictures. And actually, there are different types of systems where people try to study this. So this is an electronic system, just dirty semiconductors. So this one is ultrasound speckle in a system of randomly packed aluminum bits. So Anderson transition, of course, happens in sort of any type of sort of wave equation with randomness. So yeah, you see this looks a bit similar to what I showed before, the small fractal function, and this is supposed to be near the transition. And this is now localization of light. And again, something even similar structure. Okay, one more point I want to emphasize is that multifractality arises in problems with interaction and affects physical observables in problems with electron-electron interaction. And and it's clear why, because it affects the matrix elements. If your wave functions are strongly fluctuating, like this multifractal, of course, matrix element, you expect that matrix elements of interaction will be affected as well. In particular, Igor Gornay will speak about enhancement of superconductivity by localization by multifractality. And let me mention another manifestation is namely that it affects dephasing and scaling at dynamical scaling at metal oscillator or quantum Hall transition point. And why I want to emphasize this, because here we will see that not only those exponents, not those exponents that I discussed, will appear, but subleading multifractal exponent will become relevant. I will explain what I mean. So now what's the problem? Yeah, so this is now, again, the quantum Hall transitions, and it's the same plateaus you have seen already in several talks. And this is the rho xy, this is the longitudinal resistance. So these are different states of topological insulate, and these are peaks where this transition happens. And now this transition is sort of infinitely narrow at 0 temperature. It's a quantum phase transition. At finite temperature, it becomes finite width. And now you can ask how this width of the transition scales with temperature. And this has been studied experimentally, and you see there is a beautiful power law over like 3 decades, which shows the power law behavior of this width with temperature with certain exponent, which was like 0.42. Yeah? Okay, so now how would we understand this theoretically? Yeah? So why do we get this finite width? The finite width is because the interaction leads to inelastic processes. Yeah? The electron-electron interaction leads to scattering of electrons, and this scattering leads to what we call dephasing or decoherence. And so at the moment this happened, so that the phase coherence that was responsible for Anderson localization gets broken, and we get this broadening of the transition. So therefore, to get the width, it's a very simple logic. We just compare the localization length with the dephasing length. So the localization length scales with some local exponent, which is the exponent of the Anderson transition. The dephasing length scales with certain exponent that we have to calculate as a function of temperature.
This true is for non-interacting electrons.
For non-interacting electrons, there is no dephasing. Why would there be dephasing for non-interacting electrons? Because of what?
Phonons?
No. No phonons. It's, okay. I assume that there is only electron-electron interaction, which experimentally it makes sense for low temperature, but let's assume no phonons. Electrons and electron-electron interaction, one whole transition with electron. And one important assumption will be that, yeah, okay, so I compare these two lengths, and of course we should still calculate this exponent for the dephasing length due to electron-electron interaction, and this gives the transition width, which is just small product of these two exponents. So let me assume for a moment that electron interaction is short range. It's a key assumption here. Coulomb interaction is more complicated, and as we will see, the short range Coulomb interaction is irrelevant from the point of view of a renormalization group. So, and that's why I can analyze things relatively easily. It's irrelevant, but strictly speaking, it's what's called dangerously irrelevant. But for those who knows what it is. So yeah, typically, of course, the interaction will be Coulomb and long range, but let's assume it's screened in some way, or we consider some cool model of some other realization of these neutral particles, or we just think about mathematics and not physics and just do it purely theoretically. Yeah? Okay, so first thing what we will ask, how the interaction scales. And the scaling, we start just from scaling of simplest Hartree-Fock matrix element of the interaction. What is shown here, it's formally it's just to take two-way functions, build such combinations, later determinant, and take modulus squared. Yeah? That's basically what you need to know how it scales. And this will scale as a function of the distance between the point with some exponent. And this is again a multifractal exponent mu2. However, it's not one of those exponents that was before. And the reason is, so this is one of this, what I call subleading exponent. And this is because there is this cancellation here between these two diagrams, this one I call Hartree-Fock cancellation. Yeah? Let me show it on numerical plot. Yeah? So what is shown here is the scaling of the overlap. Actually, there are two curves here, and it's just numerical data. So one is the overlap, like when we take two-way functions and consider the overlap psi modulus squared. And this is a Hartree term. And this is the second term, which is like psi star. So this is a corresponding exchange term both appear when you take this thing and take modulus squared. So there will be two types of terms. There will be phi squared modulus, and there will be phi star, phi star. And what you see here are that leading terms scale. They scale in the same way. There is a multifractal scaling that becomes large for small distances. However, this once you subtract them, you see something totally different. There's a different scale, again as a power law, but the sign is different. So now it becomes small for small distances. It's sort of it's suppressive due to multifractality. And this corresponds to exponent, which now is sort of this exponent what we call mu2, and this has an opposite sign. It becomes smaller due to this multifractality. It's smallish at small distance. So that's an example of a subleading exponent, which will be sort of discussed later. In fact, one should go to the second order to calculate dephasing. So this is a diagram of second order of interaction. The first order, there is no inelastic, real inelastic processes. And now we have another exponent, because now there are 4 points here. There are 2 interaction lines. So it says 2 such matrix elements products. So there are the 2 exponents that appear here. One is the same as before within each interaction line, and another one which corresponds to scaling sort of between the points corresponding to this interaction line. Yeah? So this is just a scaling ansatz. So we have again done numerics and extracted from numerics this exponent. So this mu2 is the same as before, and this alpha turned out to be close to 0 numerically. And in fact, as we showed below, in fact now we know that it's exactly 0. Even though that's a complicated critical point, we don't know too much about it, but for this we can show that it's exactly 0. Okay, now in general, this exponent for this dephasing lengths and for the dynamical critical exponent will depend on this alpha and mu2. In the regime, in certain case when alpha is sufficiently large, it drops off, and this is what happens for quantum Hall transition. And so we get the exponent kappa out of this numerics, out in this analysis, expressed in terms of the exponent mu2 and the exponent mu of localization length. So we can put the numbers that are obtained from the numerical analysis of this exponent, and to get this kappa like something like 0.31, which is different from what is an experiment, and we are very happy that it's different, because that's what this is an agreement that the experiment is of course for Coulomb interaction, the existing experiment, so these two systems are in different universality classes. It would be very interesting to see such an experiment for short-range interaction. One should screen Coulomb, but it seems to be not so easy to do, but maybe we'll do it. Okay, anyway, so I just explained how this subleading exponent appear in observables in scaling in interacting problems, at least with short-range interaction. So now let me come to this another subject, namely the symmetry property of multifractal spectrum. So some years ago, well, already 20 years ago, in fact, Jan Toda and myself observed by doing the direct calculation within the sigma model that there is a nice property of the distribution of local density of states. Namely, that the distribution of local density of states, so this rho tilde is just local density of states normalized by its average value, so that average is unit. Right? So the distribution of local density of states has a symmetry. Distribution of rho, P of rho is equal to P of rho minus of 1 over rho with some prefactor. So more recently, we sort of returned to this and realized that this means that the multifractal exponent have exact symmetry. And that's because for any sort of Anderson transition fixed point, you can construct, well, at least normal usual Anderson transition fixed point or quantum Hall fixed point, you can construct the sigma model which will be critical, which will flow into this fixed point. So because of universality, everything that you define it for sigma model will be exact for exponents, and so we have a symmetry between multifractal exponents. Yeah? And so if indeed we check by numerics that it's indeed fulfilled. Yeah? And it's a very non-trivial symmetry since the probability of so large, so you can take Q, which is, for example, I don't know, 8, and then this will be -7. Yeah? So the moment like 8 is equal to the moment -7, and it means that the probability to have very large and very small values of wave functions are related. Yeah? That's such a symmetry. So basically the question that we now want to answer is the following. So what is the fundamental reason for the symmetry? Is there a generalization to other symmetry classes? So that was only for Wigner-Dyson classes. Well, actually, original work was for unitary class, and then Young generalized it for 2 other standard classes. And whether one can sort of do it for all these subleading operators, which of course requires classification of the subleading operators. And this is the assumption. This works. Now let me present the results. I will not give a derivation, but these are sort of statements. So first, classification of scaling observables. Consider n points R1, Rn, which are all close to each other. Consider n wave functions, psi1, psi-n, which are all close to each other in energy, so they may be sort of nearby wave functions in just next next level. Anyway, they all should be critical. Eh? So for each p less than 1, define the following thing. Take the Slater determinant of the first p wave function, first p point, and take the model square of this. This will be called AP. Now, take product of all these APs to certain powers, where Q can be in principle any complex. Take the average of this. So the statement is that these are pure scaling correlators of wave functions, and this is generalization of this multifractal. So if you take only A1, this will be just psi squared modulus, and this will be standard multifractal. So this product is a generalization. This includes all subleading operators. That's a very broad family. So the proof of this goes by mapping to sigma model. So if you map this to sigma model, you find the following operators in terms of sigma model, which correspond to these observables. It looks similar. It's a product of these quantities, which are D1, D2, Dn, and these Ds are minors of the sigma model matrix. So Q is a matrix, and in general, it can be a large matrix. So you can take a big sigma model, so to say, where you take this n. You remember I introduced this n, the size of the group, sufficiently big, so that you have a matrix which is kind of n by n. Well, actually, it's n by n after you take some sub-block of it, which is shown here, but let's just, it's already technical details. And then within sigma matrix, you take this, this blocks, well, it should be quadratic, of course, and take the determinants. And these determinants are these that are shown here. And you take the product to the same powers as before. And this is an exact scaling observables that corresponds to the scaling observables in terms of wave functions. So it means, so this is the exact pure scaling operators in terms of sigma model. Now the way we can prove it goes through so-called Iwasawa decomposition, or equivalently, these operators can be constructed as highest weight vectors. So let me remind you what is, or very briefly tell you how it goes. I mean, go into all technical details here. I'm not sure even if it started from the very beginning of the talk. You probably wouldn't, those who do not know would not be able to follow probably. So let me just say it very, very roughly. So the sigma model space is in general is a quadrant G over K. Yeah, so it's you take a big group and sort of divide out its maximal subgroup. So as an example is shown here, and now the Iwasawa decomposition is general decomposition of this sort, where this K is the same K. A is a maximal abelian group in G over K, and N is a nilpotent group. So nilpotent means, in terms of matrices, that it's represented by triangular matrices with 1 on the diagonal in certain representation. I mean, it looks maybe complicated, but I think everybody knows this because we all know Gram-Schmidt decomposition that is used for orthogonalization of the set of vectors, and it's just a representation of a matrix as a product of triangular and unitary. And that's exactly generalization of this to any group. So this M corresponds to triangular, and A times K corresponds to unitary. So now you can find spherical functions. So the spherical functions on this manifold of the sigma model are eigenfunctions of all G-invariant or Casimir operators like Laplace operator, and in particular RG transformation and our scaling operator should be eigenfunctions of renormalization group belong to this category. The RG is G-invariant operator. So we need to find the spherical function. So they are just determined by symmetry. It's analogous to finding spherical function on the usual sphere. The only thing that here the sphere is very complicated. It's partly non-compact, it's supersymmetric, but otherwise it's the same. So it turns out that this Iwasawa decomposition is very helpful, and because once you do it, you can find eigenfunctions which are n-invariant. In a very simple way, they are just plane waves on this abelian group A. And so these wave functions are analog of the function, of the spherical function YL, with M equal to L, and this is what is in general known as highest weight vectors. Yeah? So this can be constructed very easily, and we can show that these are exactly those that correspond to our observables in terms of wave functions. Okay, so we have a classification now of operators. So in a sense, this set of Q's, which stays here, determines a representation, and it's on this complicated sphere, so to say, analog to angular momentum for normal sphere. And now the magic comes that it turns out there is a symmetry known as Weil group symmetry, and this symmetry tells that eigenvalues of any G-invariant operator are invariant with respect to following operations. First, reflections. I can reflect these Q's. I have the set of Q's, these complex numbers that determines my observables. I can reflect them with such shift, where shifts are known, and I can permute them with the same shifts. So there is a big group, and it means that, in particular, eigenvalues of RG, a renormalization group, which means scaling exponents, are invariant with respect to this. So, in particular, this simplest example is that if you just take one Q, there is one reflection, Q, and one minus Q, and the corresponding eigenvalues should be equal, and this gives exactly the symmetry of multifractal spectrum we had before. But we have now much more. Let's take two Qs. Now we have 8 operators, and they all should have equal critical exponent. Even if we cannot calculate them, the exponent, we know that they're equal. And this can be, of course, continued. And let me show one manifestation of this, which is related to what I discussed for this dephasing quantum quality. Let's return to the simple quantity. This matrix element, Hartree-Fock type of matrix element, or just Slater determinant, two wave functions, 2 points, this A2. Consider scaling of the moments, A2 to the power Q. So in this terminology, this corresponds to this exponent delta Q comma Q. And we have many symmetries out of this, and one of those is that delta Q comma Q is equal to delta Q minus Q, 2 minus Q. Therefore, the spectrum will be symmetric with respect to Q going to 2 minus Q. By the way, the two exponents that I introduced before in the analysis of this quantum Hall dephasing are just belong to this category. In particular, it means that delta 2 is equal to 0. We have proven that some very non-trivial exponent, the square of this, is equal to 0. And this is a numerics for the multifractal spectrum of this Hartree-Fock, of this Slater determinant. And but our prediction is that there is a symmetry with respect to this line, and you see beautiful symmetry, and in particular, this should give 0, exactly like this. Yeah. So that's full. Okay, this can be generalized to other symmetry classes. So you know, in general, there are 10 symmetry classes. Already discussed it today. So each of them is characterized by sigma model living on certain symmetric space. So one can generalize the analysis, and it turns out that we can do it for other symmetry classes, but with some footnote. It goes without any complication for 5 symmetry classes, now 3 Wigner-Dyson classes, and 2 superconducting classes with preserved spin invariants, so C and C1. But for two more symmetry classes, D and D3, it almost goes. However, with certain remark. Namely, it only goes if sigma, the point is that sigma model here can jump between two disconnected parts of the manifold. There is a O1 or Z2 degree of freedom. And only if you forbid these jumps, then this applies. Our generalization logic applies, and our statement applies. And we know microscopic models where these jumps are indeed forbidden, and then we know that for this model this indeed holds, and there is a very strong consequence of this. Namely, the symmetry in this case is such that no localization may happen in these classes. So we can prove in this way that in the absence of these jumps, essentially domain walls between two manifolds in the sigma model, there can be no Anderson localization. Everything should be delocal. And this, again, is consistent with all what is known about these classes. Yeah, there are three chiral classes which contain some U1 degree of freedom in sigma model manifold. And this is more complicated. So what we say does not apply directly. And this should be in some way maybe generalized. But OK, so I'm finishing. So I try to sort of convince you that multifractality is a very remarkable property of Anderson localization transition. We have classification of operators describing wave function correlations of exact scaling operators in terms of observables and in terms of corresponding sigma models. We have a large number of symmetries of the corresponding scaling exponents, which are due to Weil group invariance of the corresponding sigma model. There are some manifestation of this in two-terminal transport observables. I did not have time to discuss it here. And there are clear sort of prospective and open questions. Namely, of course, I hope to see more numerics on this. So chiral classes remain open. And there's a very sort of major of open sort of question and research direction. Namely, what happens with all this, with all this classification of observables and maybe with the symmetries in the case of long-range Coulomb interaction that drive the system to another fixed point. Thank you.
Before the question, I just make historical remark. Paper by Anderson was left unnoticed, and the person who noticed it was Neville Mott here in Cambridge. And all what we know, localized states, extended states, localization, transition, all these coping conductivity, all this language was introduced by him around 61. Questions? Yeah?
Well, you give examples of several experiments. Now, in some of them there are interactions, in some there are not. Are they of the same universality class? Second, did they measure also transmission or spreading of wave packets?
Yeah, that's, I think, most sort of difficult question you could ask to this talk. So I show this experimental data just to show that there is an activity. Of course, in the electronic experiment, of course, there was an interaction, obviously, in the system. So it's a valid question whether it applies or not. In others, there was no interaction. It's one was optics, another was ultrasound. So their interaction should not be so important. However, there is a major problem with absorption. That all of them, So that's so that's why observation and of Anderson transition is not simple. Sort of in both in electronic and in sort of classical wave system. That's why I didn't want really to they measured various quantities, but I don't want to go in sort of real analysis of this. I think it's only sort of in the beginning.
Gentlemen, ladies, we are behind the schedule. Thank you. And our next speaker is Jonathan Keating.